Hi guys, in this video I want to talk you through two more representations that we can use when analyzing forces that'll be useful. So we talked about force diagrams, aka free body diagrams. And so for starters, think about these two examples, try to work them out yourselves. This is a person pulling two children on a sled, and we're going to ignore friction. So what is that free body diagram going to look like? And then over here, this is a dancer leaning on a table. What is the force diagram for the table going to look like? So try to sketch it out yourself. What's that force diagram going to look like? Then pause the video, and then I'll work it out in a second. Okay, so right now I'm thinking what forces cross this barrier. I'm going to draw the sled as just a dot. So there's gravity, earth on the sled. There is the normal force from the ground on the sled, and then there is the rope, tension on the sled. I know that this thing is speeding up to the right. So I know from Newton's first law that there should be an acceleration to the right. Otherwise, if there was no unbalanced force, no net force, it should move at constant velocity. So that's where that's coming from. And I am seeing like, oh, this thing is acting to the right. Therefore, like that's where that's coming from. That's where that acceleration is coming from. But is it accelerating in the vertical direction? No, when you're dragging a sled, they're not flying. So in the vertical direction, the forces should cancel out. So I might need to adjust my diagram here because I didn't really draw the forces to scale. One way to visualize this is by adding the vectors together. So I'm gonna put these vectors over here. It doesn't really matter the order that you add them, but I know that when I add the normal force and the force of tension and the force of gravity, the only acceleration should be in the horizontal direction because the sled isn't accelerating in the vertical direction. So remember, adding vectors sort of tip to tail, and the net force I'm going to draw in blue. This is your net force that's causing the acceleration. This is called a vector addition diagram. And it's sometimes helpful to figure out in what direction, sorry about that. It's helpful to figure out in what direction the forces overall act, if it reconciles with the actual motion. So if I want to sort of make this free body diagram a little bit more to scale, I should draw the force of gravity bigger. Because if I visualize the components, the force of gravity is equal to the force of tension plus the normal force. And that'll lead to this other representation. We can turn this into an equation. So if I want to just add up the forces algebraically, let's say I had numbers to this, I would take the sum of the forces in the y direction. This is a sigma, capital sigma, Greek symbol, means summing all the forces in the vertical direction. I would get, if this is an angle theta, and if I say up is positive, I would get that the normal force plus the sine component of the tension, this is theta, so sine of theta is going to get me just this vertical bit. That is one way to represent it. Now, what is this sum of forces equal to? We don't know yet, and we'll kind of return to it. There is this other half of the equation that's relevant. We're just not ready to talk about it. But it is useful to think, what does the sum of forces look like? In the x direction, it's just the horizontal component of the tension. So that is Ft cosine theta. Try out this one. I'm gonna see if I can upload that video later. Okay, so those are the two representations. There's the vector addition diagram, and then there's the sum of forces equation. And we haven't talked about what the other side of the equation is, but I want you to just keep in mind there is another half to that equation. All right, so that was the first example. Second example, if you didn't try it yet, try it. Table at rest. So what's interacting with it? Again, I know there's gravity. That's the easy one. I'm gonna ignore the symbols for now. The feeling and the feeling. So there's the person pushing downwards. I have a table over here. When I'm leaning on the table, I'm pushing it this way. But the table is at rest. So what's keeping it at rest? There's something opposing, canceling out that force. And hopefully you can guess it, that is friction. So there is a downward force Fn from the dancer on the table. And there's friction, and it acts only parallel to the surface. So that is opposing the attempted motion, because it's not moving. And so this is from the floor on the table. And now I have to I'm kind of thinking about this the entire time, but really you should start with, like, is this thing accelerating or not? It's not accelerating, so the forces on it should be balanced. So when I add up all the forces, they should cancel out. So that's how I know that the normal force, it's not just canceling out gravity, it's also canceling out sort of the vertical component of the normal force. So that's why I'm going to draw it a little bit bigger. So this is the normal force from the ground on the table. So this is the force diagram representation. I'm going to draw the vector addition diagram. If you didn't get this far, try it. Pause the video, try it. I'm just going to go up and to the right. Sorry about that. So there's the normal force. There's the force of friction pulling you, pushing in that direction. There is the force of gravity. And I know I have to end where I started because there is no overall net force. It's not accelerating. So that's why I should end up where I started. If that's confusing for you, think of these vectors as displacements. So if I walk up and to the right and down and back and to the left, I've ended where I've started. My total displacement is 0. So that's sort of the analogy, thinking in terms of maps. Here, these arrows do represent forces. There is an upwards force and a force to the right, but there's also forces that on total cancel out. So that's why we should sort of end where we started. There should be no net force. And one way to write that is F net equals 0. And now in terms of the equation, you're going to want to break it up into two parts. There's the sum of forces in the y direction, the vertical, and there's the sum of forces in the x direction. So you just go one by one. Again, I'm going to assume up and to the right is positive. So what's acting in the up-down direction? Oh, normal force is acting up, and it's the entire component of normal force. And there's also force of gravity acting down. But there's also this component of my push. So I'm going to call that my angle theta. It doesn't really matter what angle you use as long as you know what angle you're talking about. So if I use this angle, it's going to be Fn sine theta. And over here, again, just keep in mind, well, in this case, the sum of forces in the y direction equals 0, because I know that they should cancel out. So that's the sum of forces equation in the vertical direction. And then the horizontal direction, it is friction acting to the right, and I call to the right the positive direction, minus that horizontal component. And this is also equal to 0. The forces are equal, they cancel out. So if I wanted to show this with tick marks, this is equal to this. I didn't really draw that to scale. And these two put together is equal to this. If the tick mark representation kind of confuses you, just ask me about it later. But basically it's like this symbol plus this symbol is equal to these two symbols added together. These are just two more representations that will hopefully be useful and help us analyze some more scenarios. All right, bye.